So good afternoon, everyone, and welcome to today's Red Talk. I'm Allison Wilson. I'm from the Department of Statistics, and the Red Talk series is sponsored by the Data Science Initiative and the Office of Research and Innovation here at NC State. So just a couple of logistics. This talk does count for seminar credit for statistics and computer science students. And so if you need to swipe for computer science, here's the person you need to see, and he's sitting out at the table just outside. And the clipboard for statistics students is also out on the table just in front of the room here. Following the talk today, there will be coffee and cake reception just next door. In that room. And following that reception, there is a no-host social that is sponsored by the North Carolina chapter of the American Statistical Association and the North Carolina Women in Machine Learning and Data Science. That's going to be held at the Raleigh Beer Garden, which is at 614 Glenwood Avenue. Okay, so now let's move on to our speaker for the afternoon. And so our speaker today is Dr. Cynthia Rudin. She is a professor of computer science, electrical and computer engineering, statistics, and mathematics at Duke University. And her research lab is the Prediction Analysis Lab. And the research focuses on machine learning tools that help humans make better decisions, with a lot of focus in the area of interpretable machine learning. So Dr. Rudin is a fellow of the American Statistical Association and the Institute of Mathematical Statistics, and she is one of this year's Thomas Langford Lecturers at Duke University. And so with that, Dr. Rudin.
Thank you. Okay. All right, so I'm going to talk about interpretable machine learning and criminal justice. And I want you to think about the world as it is now, where they don't use interpretable machine learning for some really important problems. And what they're using is black box machine learning models. And these are models that are either too complicated for any person to understand. They're like formulas with lots and lots of calculations in them. Or they're proprietary, which means that there's some company's secret sauce, and so the calculations are actually hidden. And in contrast, an interpretable machine learning model obeys some kind of domain-specific set of constraints so that a human can understand what it's doing. So I actually have a technical definition of an interpretable machine learning model. I'll just put it up there so you can read it. It says that an interpretable machine learning model, it's constrained in model form so that it's either useful to someone or obeys some kind of structural knowledge of the domain. And I put a lot of examples of different kinds of knowledge that you could build into your machine learning models so that it's easier for a human to understand them. And so there's a big spectrum between machine learning models that are fully interpretable, where you can understand how all the variables work jointly together to form a prediction, or very loosely constrained models that have just, for example, the model decreases along one variable, something like that. So now, how does this relate to criminal justice? Let me tell you about that. So I'll tell you how I got into this, too, because it was by accident. I was working with a police officer, a set of police detectives in Cambridge, Massachusetts, and we were trying to detect crime series, which are crimes that were committed by the same individuals or group of individuals. And I'd been working on that for a while, and while we were wrapping up our project, my collaborator, who is the lead detective at the Cambridge Police Department, he said to me, "Can you help me by ranking the individuals in Cambridge in order of their usage of the police department?" And I thought to myself, I don't think I want to do that. There was a few different reasons, mostly because my lab does interpretable machine learning, and I wanted, I care about reproducibility of our results, and some of this data was private, and so I wanted to work on public data. So we decided that instead of solving that problem, we would solve a related problem to show that this could be possible. And we wrote a paper where we made our code publicly available. Everything was and it was done on public data. And so here is that paper. So the paper is called Interpretable Classification Models for Recidivism Prediction. Recidivism prediction is like predicting whether someone will be arrested within a certain period of time for a specific crime. And what this paper does is it predicts, it uses this big publicly available data set, and it tries to predict whether people will be arrested within 3 years of their release from prison. And the information we have about each person is like their criminal history and then all kinds of other information, their age, their gender, and their race, and all kinds of other information about those people. And so we tried to predict recidivism for many different types of crime, for drug crimes, for violent crimes, for just general crimes, for property crimes, you name it, and we tried to predict it. And I'll tell you the main conclusions of this paper. And remember, we wrote this, the date is important on this. So I've highlighted the date. This was March of 2015 when we posted this paper. So March of 2015. And this was before a lot of stuff has happened more recently. But so we posted that paper. And here are the main results of the paper. So the main results are that most machine learning algorithms have very similar performance across all of these different recidivism prediction problems. So in other words, and that includes the interpretable machine learning methods. So in other words, we had many different algorithms. We applied it to the same problem, like predict drug offense within 3 years. And all the algorithms tended to perform the same, including the ones that produce very complicated models that no human could understand, as well as models that produced very interpretable models that are very easy to understand. So that was the first main result. And then there was another result, which we didn't think was particularly important, so it ended up mostly ending up in the appendix, which was that the race variable was not actually useful for predicting recidivism. It didn't end up in any of our models, even though it was in the data set. So, but the fact is that it was correlated with criminal history and with age. And so if you took the rest of the variables, you could actually predict race fairly well from age and criminal history. But you didn't, once you had age and criminal history, they were actually more valuable than race, and you didn't need race in your model anymore. Okay, now I've told you that the machine learning methods have very similar performance across problems. So I want to show you what that means. What does similar performance actually mean? Okay, so what I'm showing you are ROC curves. And if you're not familiar with an ROC curve, you should just think that better performance is up toward that upper left corner. And so what these curves represent is the results from all different machine learning methods. And so this is just a list of all the different machine learning methods that we tried, okay? And some of them, like support vector machines with radial basis function kernels, produces very, very complicated models that no human could really understand. And also things like boosted decision trees in Brown, that also produces very complicated models, whereas in random forest, whereas some of the other methods produce models that people can really understand. And I'm going to focus specifically on SLIM, which is an algorithm that came out of our lab, and I'll tell you about that soon. But my point here is that all of these curves are right on top of each other. I mean, there's like two curves that aren't, like the dark and light green curves. They're not performing as well as the other methods, but those algorithms are from the early 90s. So you wouldn't expect them necessarily to do that well. But all of the other methods are like right on top of each other in terms of performance. And then the left, by the way, the left curve is just general arrest prediction. And then this is prediction for a drug offense. And so essentially what you're seeing is that all the methods perform the same. So I want to talk to you about some of the SLIM models. So the SLIM models are the blue dots. And I'm going to show you some of the SLIM models along these curves. OK, so here's one of the SLIM models. So this model this is a machine learning model. I know it looks like somebody made it up, but it's not. It's an actual machine learning model that came out from data. And the model predicts arrest for any offense, for some offense, within 3 years if the score is at least 1. And you're supposed to add up the points, like if they've had prior arrests or for a misdemeanor, or at least 5 prior arrests and so on. You get points for that. And if the points add up to more than 1, then you predict yes, and otherwise you predict no. And I want to point out that all the things in this model were chosen by an algorithm. So there were a lot of features, 60 or 70 features. It chose 5 of them. And then the number of points there, that was all chosen by the algorithm, the 2 points and the 1 points. And they're very simple to add up. And that was all done as part of, that's what this algorithm does. It chooses very simple, it creates very simple point scoring system. I mean, the algorithm is kind of complicated, right? Because it's solving the big combinatorial problem. But the models that it produces look like that. And I'm going to show you results from another one of those methods from the previous slide. This is lasso. So lasso is a very famous statistics algorithm that produces very sparse models. So I want to show you what the lasso model looks like. And lasso is known for being interpretable, but it doesn't produce models that are exactly like the one on top. So I just want you to take a look at those point scores, and you'll see that it's not quite as interpretable. I mean, even if you tried to multiply all the numbers by 100 so that you get 63 points, 15 points, that's still adding up 63 and 15, which is not nearly as easy to do in practice when you're, when you're operating, when there's a person in the courtroom and you're the judge or something like that. So even though they're the same size, there really is kind of a big difference in interpretability between these two models. OK, so I think the one on the top is not as easy to screw up in practice. Now let me show you some more of the SLIM models, OK? So this is another SLIM model. This is one of the models that predicts drug offense. And so again, you see that the algorithm would tell you to add up those points to produce a score. If the score is bigger than 7, predict arrest, otherwise arrest for drug crime, otherwise predict no arrest for drug crime. OK, and then here's another example for violent offenses. OK, and I have a set of students repeating these experiments right now on a couple of different data sets from different states. And what they're finding are models that are even simpler than these models. They're actually finding almost exactly the same results. All the methods are performing almost the same. And they're getting very, very simple models that also perform as well as the most complicated machine learning methods that we can construct that are still good. OK, and I think it's really interesting that this recidivism prediction problem admits such interpretable models, but it does, and that's the truth. OK. All right, so these are inherently interpretable models. These are not black boxes that need to be explained afterwards. These are machine learning models that are inherently interpretable. All right, so just to, I want to contrast interpretable machine learning with what's now called explainable machine learning. So there's a big chasm between these two things, which is the presence of a black box. And so interpretable machine learning, you don't have a black box. In explainable machine learning, and sometimes people confuse these terms. Explainable is a new term. It never existed before 2016. Interpretable machine learning, that term has been around for a really long time. Or comprehensible is another kind of older term. But anyway, so when most people say explainable, they mean that they take a black box and they try to explain afterward what it's doing. So this is a post hoc analysis. You have some complicated formula. You want to figure out what it's sort of doing. And so what you would do is start with a black box, and you would do something to it. You'd poke at it in some way. So you might create a model that approximates it and call that an explanation. Or you might compute derivatives of the black box and along certain concepts or certain directions. You might try to visualize for neural networks and computer vision. You might visualize what the network is paying attention to and call that an explanation. So there's lots of different types of explanations. I'm going to focus mostly on the approximation models, because that's a lot of what people are doing nowadays. They're trying to approximate the black box and say that that's an explanation for what it's doing. But these things are, I just want to make it clear, these things are really not the same. OK? So there's, I'll give you a few reasons why. I wrote a long paper that details many, many reasons why these two things are not the same, but I'll give you some of the arguments. So first of all, when you trust a black box, you are trusting the database that it was built from. I have no problem trusting complicated formulas. I trust complicated formulas every day. What I don't trust are databases, because every big database I've ever seen has had some major flaw in it. So if you take a database and you build a black box from it, no matter how much you explain it, if you trust the black box's predictions, you're still trusting that database that that model was built from. And that, I'm not sure that's a good idea. OK, another reason why these things are not the same is that when you have a black box and an explanation, that's two models. You have the black box and you have the explanation, which means you have to troubleshoot both of them. So if you're relying on two models instead of one, these models have to disagree with each other. Because if they don't disagree with each other, then you don't need the black box. Because it's the same as the explanation. So you could just use the explanation. And then that means that since the black box and the explanation don't always agree with each other, then, well, it depends how often they disagree with each other. Because if they disagree with each other fairly often, well, then you can't trust either one of them. Okay? So if I have an explanation model that's right, say, 90% of the time, well, that's still wrong 10% of the time. So if I can't trust the explanation 10% of the time, that means I can't trust the explanation, and therefore I can't trust the black box. So I can't trust either one of them. All right. So also, typos tend to be a problem when inputting data into black box models, right? If you've got to input a million different factors into a black box model and do some kind of complicated computation with it, well, the input to that model, you had to type every single thing out, and maybe you did it wrong, and that could lead to a bad conclusion from the black box. And then also, I think the reason that I care the most about is the fact that, well, if you can produce an interpretable model, why do you need a black box? Right? If I can produce a recidivism prediction model that's that big, that's just as accurate as my favorite neural network, well, why do I need to create a black box and explain it? OK, so let me talk a little bit more about the terminology here, because I really, this term explanation, I find it very, very misleading. So a lot of people use the term explanation to equate to approximation. But an approximation is not an explanation of what the model's doing. It's just an approximation of the model's predictions. OK, so a lot of people they try to create explanations that are like kind of local linear models. Like you can see, like maybe the black box is that curvy thing, and there's some local linear explanation. And then they're saying, locally, this is what the black box is doing. Now, these explanations, you can call it an explanation. It's actually an approximation. It's not actually explaining what the model is doing. And it's just trying to replicate the predictions. It's not necessarily using even the same variables as the black box model. And so it could get totally messed up. So for instance, if the black box depends, say that black box depends on age and the number of prior crimes, well, age and prior crimes are correlated with race. So it's possible that you could construct an explanation for the black box that depends on race, and then you could actually think, if you believe the explanation, you could actually think that the black box depends on race, even though it doesn't. It only depends on age and number of priors. It's just that your explanation model, it's not actually explaining the black box. It's only approximating its predictions. And that could be bad if that happened, and you concluded that the model depended on race. And you could say, well, that would never happen. Who would be stupid enough to do that? Well, nobody would do that, right? And so you could say that this would never happen, but it actually might happen, and it actually did happen. OK, so this article came out in May of 2016. So this was a year after we posted our Journal of the Royal Statistical Society paper. And this paper, this is an article by the ProPublica group, which is a news organization. And they claimed that the COMPAS model that's used throughout the US justice system for predicting recidivism is racially biased. Now, COMPAS has over 130 factors in it. It's a black box. We don't know what factors are actually being used for COMPAS. And the company that runs this model that's used throughout, this really used quite heavily throughout the justice system in many states. That model, the company makes money off of its use in the justice system. And then the ProPublica article, they showed these pairs of individuals. They showed one black person and one white person. And then they showed that those people, these are pairs of people where the black person had a lower criminal history but a higher COMPAS score than the white person. So it really looked like the model was racially biased. And this particular article launched a whole literature on algorithmic fairness and black box models. And I read this article and none of it made any sense to me. I thought, the whole premise of using COMPAS in the justice system, it makes no sense to me. And the conclusions of that article by ProPublica, that made no sense to me either. I had a completely different perspective on this issue than both the justice system and ProPublica. It was like I was living in an alternative universe here on what was actually going on. So here's what I thought. All right, so the world was sort of saying, well, we think a black box is necessary, because I was thinking, well, why would they use a black box if they don't need one? So they really must think that we need a black box, whereas our paper had already said that we'd already published. It said that interpretable models were just as good. And I thought, well, who's wrong here? One of us is wrong. I don't know who. I thought we did a good job on that paper. And then the other thing that ProPublica was saying was that this model depends on race after conditioning on age and criminal history. So they were saying that, given that the model depends on age, criminal history, and race. Okay? There's a non-zero coefficient for race. It was a statistically significantly non-zero coefficient. Whereas our paper said, well, there's no need to use race after conditioning on age and criminal history, so any reasonable model wouldn't use it. But there was also a big difference between the world and us, which is that there was a lot of money involved in using these black boxes in the justice system. And they also have quite a lot of data, whereas we didn't even have a grant. So it's a different situation. All right, so luckily, the ProPublica group made available some data. In particular, they provided COMPAS scores. They provided outputs of the black box model from a particular county in Florida so that we could do some analysis here and figure out where the discrepancy actually was. OK, so what we did was we took that data and we put it into the latest machine learning method that came out of our lab, that was coming out of our lab at the time, which was the Corals method. OK, so COMPAS has this fancy name, whereas our method was just an optimal decision tree method. It's called certifiably optimal rule lists. It was just a method that produces logical one-sided decision trees. And we took the data from Florida, and we put it into this method, and we were thinking, I wonder which one is more accurate, the black box or the interpretable machine learning method. Now, the interesting thing about Corals was that it came up with a machine learning model that was so small that it could fit in the corner of a PowerPoint slide. And this is the model. That's the whole model. So it basically says if you're young and male, predict arrest this is within 2 years. Else if you're 2 years after leaving the police station. Also if you're a little bit older and you have a couple of priors, then predict arrest. Else if you have more than 3 priors, predict arrest. Otherwise, predict no arrest. That's the whole model. That's all. That's what it says. And so you'd be thinking, well, this proprietary model that is being defended in lawsuits and so on and so forth versus that, which one's more accurate? And you'd think it would be that one, but the truth is they're exactly the same. OK, so what I'm showing is accuracy on the Florida data for COMPAS and Corals. And the different colors are different subsets of data. They're different folds of data. And so you can see that across folds, you're seeing basically no difference in accuracy between the black box and our method. And what's really interesting is that even if you try a whole slew of different machine learning methods, they all perform the same too. And that includes boosted decision trees and support vector machines with Gaussian kernels and random forests and everything else we can get our hands on. You're just not seeing any more accuracy from the black boxes. So the black boxes are sort of several of these algorithms, and then Corals, again, just produces models like that. OK, so world versus us. I still think we were right. OK, so let's look at the race question. ProPublica says COMPAS is racially biased. After conditioning on age and criminal history, you still need race. And we said, no, nobody would do that. But that doesn't mean COMPAS doesn't use it. So why would ProPublica think that COMPAS depends on race? So here's what ProPublica did. Okay? They showed that the false positive and false negative rates of of these of COMPAS varied by race. Okay, so whites and blacks have different false positive and false negative rates. And they suggested in their article that this might not be a good comparison because the blacks and whites in Broward County, Florida are the people who are being arrested are very different from each other. The blacks are younger and they have more priors. The whites are older and they have fewer priors. And so they said, okay, what we should do is condition on age and number of priors and re-examine this question. And so they did that, and they conditioned on age and number of priors, and they still found a linear model with a significant race coefficient, okay? So they still said, okay, it depends on age, number of priors, and race. And then they concluded that COMPAS depends on race. Okay, so let me do that again, but with a little bit more detail about what I think they did. Okay, they showed that false positive and false negative vary by race. This is a property of the data, not necessarily the COMPAS model. So in Broward County, the blacks in the database are younger and they have more priors, okay? So even if you just have a model that uses only age, you're still going to see a difference between the false positive and false negative rates. And so they thought this might not be a good comparison. Good idea, I agree with them. So then they created this separate model that approximated COMPAS. And they found this model that had a significant race coefficient. The problem is that I think they explained COMPAS wrong. I don't think COMPAS has a linear dependence on age. And so that's why I think their conclusion is wrong. OK, so the issue is that they just didn't check the assumptions here. Okay, and we've been working on this analysis that tries to uncover some of COMPAS's secret sauce. Oh. Okay, all right. Okay, I thought that was me. All right. Okay, yeah, so, yeah. All right, so we've been trying to figure out what's actually inside COMPAS. Because if I'm going to go to the trouble and say COMPAS, there's something wrong with COMPAS, I actually want to know what's inside COMPAS. If this company is going to sell people this model and say that they're better than my interpretable machine learning models, I want to know what the heck's in there, right? I want to know their secret sauce. So on the next slide, I'm going to show you some of what I think COMPAS's secret sauce actually is. OK, so here's something that I think is true about COMPAS. So COMPAS, by the way, it's got 137 factors, and it's proprietary. And most of the data are not public, okay? Because a lot of it's survey data. A lot of it's questions that the people have to answer. And COMPAS's manual claims that there is a linear dependence on age. But that's not what the data says. OK, so our conjecture is that the COMPAS general recidivism model is a nonlinear additive model. And we think its dependence on age in Broward County is approximately a linear spline. So not a linear model, but a linear spline. And there's actually two COMPAS models that they provided scores for. This is the general general recidivism score, and then there's a violence score. And I think that one is also, its age component is approximately a linear spline. OK, so how did we get this? So the best way for me to show you how we got it is to plot the data. So I want to show you this. So what I'm plotting here is the COMPAS violence score versus age. And there's a dot for every individual in the database from Florida, from Broward County, Florida. And what you can see here is that there's kind of a sharp lower bound for the COMPAS score for each age group. There's a few outliers, which are in red. But everybody else lies above this kind of curve over there. And if you look at the people who are on the very bottom of the curve for each age group, you'll find out that a lot of them, most of them, have no prior criminal history. There's nothing in their record that we found that would indicate a risk factor. And so we believe that that curve there, we think that that is the contribution of age to COMPAS. And that curve is the linear spline that I showed you on the previous slide, that red sort of curve. So that's the violence score, and this is the general score. And I'm going to zoom in on those curves right here. And you can see the parts of the linear spline right there that we created. And there's a lot of individuals who lie literally right on that thing, right in those gray dots. The shade of the gray dot, which you can kind of see, is the number of people who are right on top of that dot. OK, now what ProPublica did was they modeled these as lines. They created a linear model. And you can see that that's really not a great approximation, especially at the younger ages, where there's a lot of individuals in the database at younger ages. And so these linear approximations, it's a particularly bad fit where most of the people in the data set are at younger ages. OK, so ProPublica's analysis isn't right. COMPAS's manual seems wrong because they claim that there's a linear dependence on age. And then we said, well, even if ProPublica's wrong, and if COMPAS's manual is wrong, maybe we can still try to figure out whether COMPAS depends on race. So we said, all right, what we're going to do is we'll subtract off what we think is the contribution of age to COMPAS, which are those linear splines, and then run machine learning methods with and without race to see if they need race to predict COMPAS well. And I don't want to get into too many details about this, but the bottom line is that the machine learning methods do not need race to predict COMPAS well. So I know this is a lot of information to process. So I'll tell you the only thing you need to look at is the fact that these pairs of numbers are very, very close to each other. Because what I'm showing you are a whole bunch of different models with and without race. And you can see that their predictions are very similar to each other. And the top table is for the general recidivism score, and this one is for the violence score. So for both scores, we're not seeing any indication that they depend on race other than through age and criminal history, which are correlated with race. OK. So again, I still think that that this was correct, that this logic still makes sense to me. But if COMPAS doesn't depend on race, what the heck does it depend on? If it doesn't depend on other factors correlated with race, right? It depends on age and criminal history. If it doesn't depend on other factors correlated with race, what does it depend on? And I don't know. But one thing I can tell you is that I didn't yet discuss what is possibly the biggest reason not to use a model like COMPAS. And the fact is that humans are just not very good at inputting data reliably. So if you have 137 factors, if they're all calculated by hand for each survey, they're entered into the computer by hand for each survey, then even if you have a 1% error rate, then there's a 75% chance of at least one typographical error on a survey. And so that information, you have this huge giant mess where the taxpayer dollars are paying someone to sit there and collect all this very private data, making typo after typo, and it's really difficult to check. And the information goes only to one source, and so what does that lead to? It's bad decisions. And there are cases where people have been given extra years of prison time, years of extra prison time, because of typographical errors on their COMPAS scores. So this is the case of Glenn Rodriguez, and this was written up in the New York Times. And this was a very famous case because there was a typographical error on his COMPAS score in his criminal history, the criminal history part of his score. And then he was denied parole. He was in prison for a crime that he committed as a kid. And he was in prison for 17 years. And he was finally up for parole. And he was a model prisoner. And they denied the parole because of well, they think it's because of the typo. But yeah, and there were a lot of court cases as well trying to determine whether the fact that these models are proprietary violates due process and so on. OK, so we were trying to look at the Florida data to figure out how often these typos might happen. And we found some strange inconsistencies in the data. So what I'm showing you are some of the individuals in the database. And what's really interesting is that, all the score is private. That data is really private and proprietary. But all this criminal history data, it's like the phone book. It's completely public. It's so ironic. Anyway, so what I'm showing you are individuals with very low COMPAS scores. So these are COMPAS scores of 1 and 2. That's the lowest score you can get. It's the violence decile score, which goes from 1 to 10. And then this is the number of prior crimes these individuals have. And then these are examples of some of the prior crimes they've had. So for instance, robbery with a deadly weapon, aggravated battery with a deadly weapon, aggravated battery, great bodily harm, whatever, attempted murder in the first degree, battery on a law enforcement officer. And so these people it just surprises me that these people would be given the lowest possible COMPAS score. So there's something in the data that's not right. And this list is long. I mean, I only showed you the beginning of it, but it goes on and on. So here's some more people. So these are people with COMPAS scores of 3 and 4. And this is the number of their priors. And you can see it's just, aggravated battery on a pregnant person. I mean, woo! So it really surprises me that there are so many data issues. And then we were looking back at ProPublica's article where they had all these very convincing graphics that would really lead you to believe that COMPAS was racially biased, right? They had all these pairs of people where, a black and a white person with where the priors don't seem to agree with the COMPAS score, and you wonder how that could happen. Is that racial bias? And it turns out that we looked through the database, and we found a data problem with at least one person in every pair of these examples that ProPublica picked. And so essentially, these examples were cherry-picked to make the algorithm look racist. But in fact, the source of the problem seems to actually be typos combined with a lack of transparency. So if you're a journalist, this is, in my view, a pretty bad set of mistakes. But that's what appeared to have happened. OK, so the current state of affairs right now is that human judges are biased black boxes, and that's what we're relying on. We're relying on human judges. And even when humans explain their reasoning processes, it still may not be the true reasons that they made their decisions. And humans also cannot calculate risks from large databases in their heads, right? They're relying on their own expertise rather than using evidence-based practices if they're not using these risk scores. If they are using the risk scores, well, then they might be using COMPAS, which is a black box with possibly incorrect documentation because they claim a linear dependence on age. It's not reliably computed very clearly, but there's also financial incentives to use these black boxes, which is why they're being used, I assume. Now, COMPAS, I'm not the right person to decide whether COMPAS is fair, right? That's not I'm not the right person to judge that. But I can say that it has a kind of procedural unfairness where typographical errors can end up making huge life-changing decisions for people, and I don't think that's fair at all. Now, right now, California is moving toward a no-cash bail system, possibly using COMPAS. There's a recent article on that, although I'm sure there are probably more recent ones than that. ProPublica's seriously flawed analysis is still highly cited and respected. I've heard it given lots of praise. And then more recently, there's been an article in the New York Times from individuals at MIT and Harvard and other places calling for the elimination of all statistics for risk assessment for bail decisions. And so they're actually saying that we should remove evidence-based, the statistics from altogether from the courtroom. And they had some interesting reasons, but the problem was they didn't provide an alternative. So if you remove all evidence-based, if they're saying, oh, the data are racially biased because, because there are more young black people who have longer criminal histories because police hunt down black people. That's kind of the crux of one of their major arguments. But the problem is that if you remove the evidence-based, if you remove the models, then what you're left with are the judges. And the judges can see the person's race directly in front of them. So you're not helping that problem. And then also, if you're working with models, you can actually correct some of that bias. You can actually work with it to try to help fix it. Whereas if you just take away all of the evidence, then you're stuck with these human judges, which again are biased black boxes. And it's very difficult to undo problems that way. No judge can accurately compute risk scores in their heads, right? That's why we started using statistics in the first place. This would bring us back, like removing all statistics from the courtroom would bring us back, back about 100 years, to be honest, when we started using evidence-based risk scores in the courtroom. I think, so the article, like I said, they didn't present an alternative, and I think it's fine to criticize these risk models, but you can't say no to them unless you present a better alternative, which they didn't do. Now, so Brendan Garrett and Sarah Desmarais and I wrote a response, but I think our response went largely unnoticed, and there's actually, I was just looking at the signatures on that Harvard-MIT article, and there was a huge number of signatures. I should mention one of the authors of that article was the head of MIT's Media Lab, who has now resigned for issues with the Epstein scandal. Okay, now, so right now, as we speak, the academic interest in fairness is huge. There's a lot of people working on how to embed fairness criteria into machine learning models. Interest in explainability of black boxes is huge, but unfortunately, there's been little interest or expertise in actually designing models that are interpretable, that allow people to see directly the joint relationship between the variables that form the prediction. And these would provide like some technical solutions to some of these problems, both the black box and the bias, because you can embed fairness criteria into these models as well. But unfortunately, people are not paying attention at the moment. So what I'm essentially suggesting to do is to replace something like this with something like that. Thank you.
So did you get responses or reactions from both the manufacturer of COMPAS and the publisher?
Okay, so the paper that I'm presenting was actually accepted to the Harvard Data Science Review, and they asked people from COMPAS and ProPublica to comment, as well as a whole bunch of academics to comment. And so we've received 4 comments so far. The ProPublica people refused to comment. The COMPAS people are going to comment. So we will get responses from them that they're slightly overdue, so we'll find out what they say. Yeah.
This is a similar question, but how have you tried to advocate for this? Like, this is the second time I've seen a talk that touched on this topic from you locally. So how are you trying to reach out and or are you trying to kind of push this more to these parties, the New York Times and the ProPublicas? I don't know if this is the same question as what he asked, or is there any other way that you're trying to be more aggressive, or are you just kind of taking a passive, let's publish it approach and see what happens?
Yeah, I mean, so I'm not a company. I don't have a media department. I'm just a machine learning person who likes to write algorithms, and I ended up in this field by accident. So, I'm not somebody who knows how to go and get my stuff into the New York Times, right? So for example, our response that Brandon and Sarah and I wrote to the New York Times piece, the New York Times wasn't interested in publishing it. We published it in a different venue. So I think if you don't say things that people want to hear, like the things that I'm saying, they're not things people want to hear, that it's much harder to kind of get the word out. I think it's much easier, for instance, for ProPublica to publish their piece, which says this thing depends on race, than it is for someone like me to publish and say, hey, you guys didn't need this model anyway. Why are you using it? And by the way, it probably doesn't depend on race. So I think that's part of the problem. I'm doing my best. But like I said, I haven't been that successful with getting that message out as far as I want. Mm-hmm.
So a question for you. One of the things that you showed empirically that a lot of the machine learning methods and your interpretable method work approximately the same. Is that provable?
Yeah, actually we have a paper. I don't know if I have a slide on it here, but do I have a paper? I mean, we're working on a few different things. Actually, yeah, okay, I can tell you about that. So I have one paper where we're posing a theoretical reason why a whole bunch of machine learning methods would perform the same, and because this is true for a whole lot of different problems. It's not just recidivism prediction. There's, a lot of medical problems work exactly like this, where it doesn't matter which machine learning method you use, they all perform the same. And so we have a technical argument called the Rashomon Set Argument, which is that there are many cases where there are many data sets that permit quite a lot of good predictive models, equally good predictive models. And because there's a continuum of them, then within this sort of sea of good models, there's probably one in there that's interpretable. And you can use approximation theory to kind of get to that. And so that's what that one paper does. And the other thing we've been trying to do is construct neural networks that are interpretable, because even for computer vision problems, the computer vision problems that's where the deepest of the deep, you need to have that. But we actually have a paper this year in NeurIPS, a spotlight paper in NeurIPS on an interpretable deep neural network for computer vision. So even computer vision problems permit some level of interpretability. I can talk to you about that a little bit more if you want to hear it. Okay, so computer vision problems are not like criminal recidivism prediction problems. Like computer vision problems, images, they lie along a very narrow manifold in pixel space. So if you perturb even one pixel in the space, you see there's one pixel that's off on that rose, and that takes it out of the set of natural images. That's no longer an image you'd see in reality. And so dealing with images on like narrow manifolds of these high-dimensional spaces, that's very different than dealing with other kinds of problems. And so we've been trying to design this deep neural network that's still interpretable. And so the way it works goes kind of like this. We have our network working on bird identification, because I don't know anything about birds, and so it's really useful to have the network explain the birds to us. And so this is a clay-colored sparrow. The network is trying to explain to us why it thinks that bird is a clay-colored sparrow. And so it's highlighting different parts of the bird here, and it's saying that that part of the bird looks like this other part of this other bird, which is a prototypical clay-colored sparrow. And so it's doing what's called case-based reasoning, which is a classical kind of interpretable model. It's kind of like what real estate agents do when they're pricing your house. They go, oh, this aspect of your house is like that other house, and this aspect of your house is like that other house. And so I'll combine the prices from those houses to produce your price for your house. And so that's what this is doing with the birds. It's saying, I think this part of the bird looks like that part of this bird, and that's a prototypical clay-colored sparrow. And it's actually doing a little bit, and because the network is saying this looks like that, this looks like that, this looks like that, so we decided to call the network this looks like that. It's called this looks like that. And what it actually does is it takes the image and it highlights the different parts, and it says, I think you look like, I think that part of the image looks like that prototypical, head of this bird, that's a prototypical, whatever, red-bellied woodpecker. And then there's two numbers that get computed. One number is how similar the two things are. So here, this is very similar to that. And so it gets a very high similarity score, which is the 6.499. And then there's also another number, which is how important that picture is for representing that red-bellied woodpecker class. So it's how similar this is to that, and how important this is for representing that class. And then there are 20 prototypes per class. And so it multiplies the numbers together for each prototype, adds it all up, and then this is the evidence for that bird being a red-bellied woodpecker. And you can do it for all the classes too. So this is the network trying to get as much evidence as it can for the next class, the red cockaded woodpecker class. And you can see that the red cockaded woodpecker doesn't have a red head. And so it just can't, it has similar feathers to our bird, but it just can't gather enough evidence for that class to kind of give it a higher score. And so, so our network votes for the red-bellied woodpecker class, which is correct. And this particular bird data set, this is actually a benchmark data set in computer vision. And the way the network works is that you take a black box, your favorite black box, and you add a prototype layer to the end of it to make it interpretable. And so even if the original black box is that's the accuracy of them, and then if you add the interpretable bit on the end, you actually get approximately the same accuracy. And then if you combine a bunch of interpretable networks together, you can actually get an accuracy that's like 84%, which is on par with some of the best neural networks that exist currently for this particular data set. And since it's a benchmark data set, we actually know what the state of the art is on these accuracy scores. And we still maintain interpretability when we add them all together, because just instead of having 20 prototypes per class, we just have more prototypes per class, and it's still interpretable. And so it just goes to show you that that you can, as far as I can tell, you can always add some level of interpretability to these machine learning methods and still maintain accuracy. This question back there?
I'm just curious about this question also. But why the academics still have a high interest of the explainability of the black box rather than going to this interpretability, whatever the term is, hard to pronounce. Why is that? Is that because this route is not applicable to all situations, or is that some other reason that prevent this to be more popular?
I wish I knew the answer to that. I mean, I had a funny situation where, let's see if I can find the slide there. No, I don't have it. I mean, I had a funny situation once where I wrote a letter to an editor of a special issue, and we were competing in an explainable machine learning competition. And we sent in an inherently interpretable model, and you were supposed to send in an explained black box. And we said, forget it, we're going to send an interpretable model. So I sent a letter to this guy for this special issue saying, hey, is this applicable for your special issue? We have an interpretable model for this data set. You don't need a black box. And he sent me an email back, and he said, no, your stuff is not eligible for the special issue, but can you send me the data set? Because I'm really interested in explaining black boxes, and I want to use it for explaining neural networks. So I mean, even people who know that the data set doesn't require a black box, they still want to create a black box and explain it. And why that is, I mean, I have no idea. That was just bizarre, So, and this is somebody at Stanford, so it's not, it's a lot of people who are really invested in trying to sort of poke at these neural networks and explain them. I mean, I think part of it is that it's much easier to explain a black box than to create an interpretable model, right? These explanations, all they need to be is derivatives, right? So you can write a paper with 2 equations and a whole lot of images, and you've explained the black box, right? So it's less math, it's less work, it's just, oh, we've uncovered something really cool about the insides of this thing. So it could be just that appeal. There are reasons to use black box models, right? People want to keep them proprietary, and that's a good thing in some cases, right? If a company wants to keep your model proprietary. But then in that case, I mean, then explaining it's actually really difficult, right? Because they're not really meant to be explained. Yeah.
I'm curious about if, in your opinion, simpler model necessarily means more interpretable model. I'm just thinking of, I mean, you are giving us an example to show us what explainability means versus interpretability. But if we were forcing for the model to be simpler, and we were ending up with, maybe fewer features
Yes, so interpretability has to be domain dependent because, for example, with neural networks, with computer vision problems, a sparse decision tree on pixel space is not interpretable. It's just not. Sparse decision tree on criminal justice data, great, but not for computer vision. So you have to think of each domain and work in that domain. So this is what we came up with for computer vision, but that's not the only thing you could do in computer vision. But this is our definition of explainability, it's that it can do case-based reasoning. And I think it just depends on the domain. I showed you some examples earlier where the models were equally sparse. Yeah, so this is an example where the models are equally sparse, but I think one of them is more interpretable. And I'm willing to have people argue with me, but yeah. It's just some level of constraint, right? Interpretability is some level of constraints on your model that allow you to sort of understand its inner workings.
So I had a question about where you had early on, you looked at the database and you showed that the collection of the data had a lot of errors in it because it was going from written data into digital data. And can you attack or can you then go after the COMPAS by looking at just the way the data was gained from it, that it has a lot of, it's error prone?
Yeah, so that's how we were able to find all those examples. So the examples that we found, what we were specifically looking for, let's see if I can go grab that. Yeah, we were specifically looking for cases where there was a low COMPAS score and a big list of criminal history, right? Because every model that we have says if you have a long criminal history, you should have a high risk score. And so that's how we specifically found all these individuals. Was for that. I mean, you can also find people in the other direction. You can have people who have a COMPAS score of 10 and they have almost no criminal history. But you can say that was due to, oh, you're missing some criminal history data, or oh, maybe they had some other factor on their score that you didn't, maybe some psychological assessment that led the score to be higher. So you could explain mistakes in that direction that way, but you cannot explain mistakes this way without typos or some other data quality issue. Yeah.
I was wondering if you could clarify, is your argument for where ProPublica went wrong in their analysis, is it that you don't agree that their claim is supported that the COMPAS model creates disparate outcomes for people of different races? Or is it that you don't think race was an explicit factor in the model? Because a model could not use race to make decisions, but still create disparate outcomes for people of different races. And that was one of the main takeaways. It's sort of if it walks like a duck and it talks like a duck, I don't care if it was actually considering race, but if the outcome of that is still creating more harm for one group than another, then that still matters.
Well, it's always going to create more harm for blacks than whites, even if you use age, right? Even if you use age alone and create a model that just makes a cutoff for age, that's going to have a worse impact on blacks than it is on whites because the blacks in the database are younger. So the question of whether or not you're allowed to use age is something that I'm not qualified to assess because I don't know whether that's fair. It depends on what you're using it for. But what I am qualified to assess is that ProPublica's analysis was wrong because they claimed that this particular model depended on race in addition to age and criminal history. And that part of the analysis, I believe they explained a black box, they explained it wrong. And that's what my...
necessarily the outcome of what they found that you would dispute, but the explanation that they gave to that outcome?
Well, the fact is they blamed the COMPAS model for it. And what they could have done is blamed the data for it because this is really a property of the data and not the model. And that's where I think they went wrong.
But one interpretation of a model is a trained model, right? You can't, sure the model might be updated, but the model that was used in practice is a model plus a data set. So.
But why didn't they then do the same, say the same thing for the Arnold PSA and all of the other types of risk scores that they could have chosen that all depend on age and criminal history. They didn't do that because those models are transparent, or they're at least partially transparent. And that's why they didn't look at those ones. I mean, if they had said something like, all of these risk scores, they all depend on age and they all depend on criminal history, and we don't think that's a good idea. Okay, that's a reasonable thing to say. But to simply say this particular model is a black box, and it, and it's racially biased. Even if you consider age and criminal history, it still depends on race. That's the part where they went wrong.
Did COMPAS ever reply to the article?
Oh, to the article I'm presenting?
Not your article, but the paper.
The ProPublica?
The Republic.
Yes, they did write a response. And then that started a giant war on what definition of fairness to use, because COMPAS's argument was that ProPublica used a definition of fairness that didn't favor them, right? They claim that, they claimed essentially that as long as you're, if you condition on age and criminal history, then you're getting the same, the same scores for blacks and whites. And so they just said that ProPublica essentially used the wrong definition of fairness. And so there was a lot of back and forth. A bunch of criminal justice people came in and said, no, ProPublica should have contacted at least one criminologist before they wrote this. This is not okay. So there's been a lot of back and forth on this. Yeah, and I think it all just depends on your definition of fairness. And nobody's settled on a definition. No one has settled on a definition.
Hi, so Cynthia, you are likely familiar with Dr. Christiane Loom's work with the Human Rights Data Initiative, where she looks at exactly what you're talking about, where the underlying data can really be the main issue because of biases that are inherent in this exact type of data. One, due to human error, but also due to the fact that what you're interested in assessing is whether or not there will be a crime committed. However, police data assesses whether or not a crime was reported. And so that's one issue. So these people, I do not know what typo could possibly override attempted murder and beating up a pregnant person, but there's those types of typos, but then also you have these self-propagating biased models that then send police back out into the same communities where they have already assessed that there was a crime committed, and therefore then they find more crimes. And then they are not looking for crimes in other areas, and the same thing, they're not looking for crimes among other people. And then did this list of people commit another crime, or did they get arrested and convicted of committing another crime? So it just, again, I really appreciated your point about the fault line a good deal with the underlying data that's being used to create these models. And so I think that goes back to part of what you're talking about, in that those biases would lead to issues in any type of model, but at least if you're using an interpretable model, then you can point to how and why you made the decision. And then my personal opinion is that if you are looking at a black box model and you are taking the human factor out of making a decision that affects a human life, I'm not a fan of that. So I'm not a fan of that. If you take the human factor out of making a decision that affects a human life or death or well-being, then you're putting a lot of reliance on algorithms and data that may be flawed, and it takes responsibility off of the person that is making that decision as to whether or not to put that person in prison, or to make that particular arrest, or to go back out and make another type of decision that affects a human life. So I think it's a fascinating discussion today. Thank you so much, and it really points to when we start thinking about using these types of methods in the human domain, there's really a lot of factors that really have to be taken very seriously as we put these in place. And if things are interpretable, then we can point to what we're assessing.
Exactly. One thing about having the human in the loop, which these were designed for human in the loop, right? They were not designed for human out of the loop. And the thing about the point scores is that it's much easier to calibrate information that's not in the database with the model if you can see the point scores and that they're small and that they make sense. You know what I mean? So if the judge has another factor they want to consider, well, how many points is that worth relative to these things? And they can put it in. And that's actually helpful in healthcare situations as well. If the doctor wants to treat the patient a little bit differently, then they have the ability to kind of calibrate the scores with that extra information. And then, let's see, well, the other thing I was going to say, something about the data and the fairness. So we've been trying to kind of redo this analysis with new data sets and with our new knowledge that we have from all of the literature that's been coming out in the last few years. And we've been kind of changing the types of things that we predict and the types of features that we are using. So for instance, we might have in the past used prior arrests, but now we use prior convictions, right? So you're not going to undo all of the biases, and you're still not going to undo the missing data problem, but you can at least use data that could be more qualified, like to be part of these assessment tools than not. And then hopefully I was hoping that we would find kind of proxy problems where, you know, maybe predicting arrest is more imbalanced, but predicting arrest for X might be arrest for violent crime. Maybe that's more fair. And so maybe we should leverage the violent crime prediction to help with the regular arrest problem. So I was hoping that we could kind of change the problem around to help make it more fair. So far, not so good. So far, the fairness issues seem to arise in most of the different problems, but that's at least something that we can try to solve by looking at different data. Mm-hmm.
So since there are some other events happening at specific times, let's go ahead and close the questions and thank the speaker. And if you do have additional questions, we do have some refreshments next door before you head off if you want a beer at 5:30. But so anyway, let's thank Cynthia again.